Thirdly, we will talk about belt drives capacities to transmit power. There should be a restriction on the maximum effective tension to avoid slipping. FEC, the greatest possible tension at the critical slipping condition, may be written as FEC equals 1 minus 1 over exponential F multiplied by alpha, all multiplied by F1. The maximum stress, sigma maximum, shouldn't be more than the allowable stress of the belt, the squared bracket sigma, that is, in order to prevent fatigue failure and to guarantee that a belt has adequate fatigue strength and service life. Sigma maximum equals sigma 1 plus sigma B1 plus sigma C must be less than or equal square bracket sigma. Therefore, sigma 1 must be less than or equal sigma or allowable stress, the square bracket sigma, minus sigma B1 minus sigma C. Since F1 equals sigma 1 multiplied by A, we then have FEC equals the allowable stress, the square bracket sigma, minus sigma B1 minus sigma C multiplied by A, then the other bracket 1 minus 1 divided by exponential F multiplied by alpha. This is the maximum effective tension that may be used without experiencing slippage or fatigue. The maximum effective tension and belt speed are the factors that determine how much power a belt can transfer. When we replace F with a comparable V belt coefficient of friction FV, we obtain the following basic power rating of a single standard V belt. B naught equals FEC multiplied by V divided by 1000 equals allowable sigma in squared bracket minus sigma B1 minus sigma C multiplied by A and V multiplied by 1 minus 1 exponential FV alpha, all divided by 1000. The power or the basic power rating B naught is in kilowatt. Under particular test circumstances, the fundamental power rating that one standard V belt can transfer is determined. The test scenario calls for a somewhat long belt to convey a constant load while running on sheaves of the same diameter. This lecture only contains data for type A, B, and C V belt due to the space restrictions. Standards or design handbooks may include comprehensive data about different belt kinds. This slide shows the basic power rating of single standard type A, B, and C V belts as a function of a small sheave pitch diameter and choosing rating speeds of 700, 1450, and 2800 RPM. The pitch diameters of small sheaves are given by the abscesses of the points in the diagram and can be referred to in table. By interpolating the basic power rating at different rotational speeds may be found. In practice, correction factors are used to recognize departures from these particular test circumstances. As the speed ratio rises, a particular belt can support more power. To account for this, the basic power rating is increased by the transmitted power increment B naught shown in figure. A correction factor K alpha is included for contact angles other than 180 degrees because contact angles have an impact on frictional force, which in turn affect transmitted power. The correction factor K alpha may be set to 1, 0.92, 0.82, or 0.69 respectively for contact angles of 180 degree, 150 degree, 120 degree, and 90 degree. By interpolation, the correction factor K alpha for additional contact angles may be found. Similar to this, a belt length correction factor KL is added if a belt length is different from the prescribed belt length when the basic power rating is achieved, as shown in figure. The actual power rating of a single V belt is modified as follows after accounting for this adjustment factor.